So in this video, I'm going to try to explain cylindrical coordinates, three-dimensional cylindrical coordinates, and I'm going to begin by making a parallel to the 3D Cartesian system. So x, y, and z, this is what we saw in 3D Cartesian. And now we have components s, phi, and z. And right off the bat, we can make a comparison between the two systems because we see that there's a similarity. That similarity is the z components. So if you understand z in one system, it's the exact same z in the other system. And the second similarity, this goes back to the polar system. I'd like to think of the 3D cylindrical system as two-dimensional polar plus the z from the Cartesian three-dimensional system. So these should be familiar. S, phi, and z's. We have s and phi from our two-dimensional polar system and z from our three-dimensional Cartesian system. Okay. So now we can go on and start getting a graphical representation of this system. So we have our axes, so that would be our z, our x, and our y. And we're going to define, just pick some points in space, and then we are going to project this point into the xy plane. We can go down a little further, just so we can get some symmetry going on here. Okay. So this distance from the origin to the original point is known as r, and the distance from the origin to the projected point in the xy plane is called s. And you can recall that we defined s in our two-dimensional polar system, and the angle from the x-axis to s in positive increasing direction of phi is known as phi. I think I said that weird. And this is z. So we're not going to talk about this angle, but this angle right here will become important in another coordinate system. So let's highlight the components here. So we have our s, which is defined as the distance from the origin to the projected point in the xy plane. We have phi, which is defined as the angle from the x-axis to s, and then we have z. And that is our cylindrical system with our cylindrical coordinates explained. And now we can sort of define a relationship between our x, y, z in terms of cylindrical components. And that's, if we remember a polar, it's pretty simple. So we had x was equal to s cosine phi. I'll read that a little bit better. S is equal to cosine phi, y equal to s sine phi, and z is just z. And now we want to go the other way and go from our Cartesian to our cylindrical. And if we remember, if we sort of go back to our two-dimensional system just to see the relationship again a little bit better, we'll have an axis system. Remember, this is two-dimensional because we're just looking at the xy plane. And we'll just rewrite this. So this is the projected point, and this would be phi, and this is s, some distance y, and this is some distance x. So we can define s in terms of x and y. So distance formula, x squared, or Pythagorean, is equal to x squared plus y squared. So s is equal to the square root of x squared plus y squared. So we've defined s in terms of x and y, and we can define phi also using trig. So if we can recall our SOHCAHTOA, then we can see that we can use this relationship here, where tan phi is equal to the opposite, which will give us y over x, and we can solve for phi by using the inverse of tangent, which is x over y. And so we've defined s in terms of x and y, and phi in terms of x and y as well. And then z, our last little component, is just z, and that's already in terms of Cartesian components. So we'll highlight these, and highlight this one. And we'll highlight this one. So we've found s, phi, z, as well as, go back up here, x, and z. In our next video, we'll explain the unit vectors of these systems, of this system. Just get everything in too small. One big picture. Hopefully you can see that.